Hi everyone. So we'll be going through the Leetcode Weekly solutions. So this is the first session. This is actually quite easy. So we're given an array R's in which we have to count the number of pairs I, comma j such that R's of I plus R's of j forms a complete day. Where the definition of a complete day is exact multiple of 24. So we just need to pick two different indices whose sum is a multiple of 24, and we have to count number of such pairs in the array. Right, so this is the first question, and the constraints are quite low. So you can do an order and square approach. You can go through all I and j to check if their sum is divisible by 24. So here the solution is quite simple. So we'll go through all the pairs I j. We're starting the next inner loop from j plus I plus 1. Otherwise, you can start it from 0, and at the end you'll have to divide by 2. You have to just check r's of I plus r's of j to 24 is equal to 0. This is just a brute force solution. So yeah, that's it for the first question. So this is the second question. It's the same question, only they have changed the constraints. So it's 5, 10 per 5, the length of the array. So you cannot do an order of n square approach here. We have to find a better approach. And so we need pairs who divide by 24. So let's consider, we can go to, let's see, we are at the index I right now, and we have some info about the numbers behind that. We need to know how many j's are there before j less than I, such that ai and aj can form a pair. So we need to know, let's say this number is ai, and we have to know a sum by aj. This should be, this should divide by 4, right? Right. So we need, let's say this ai can be represented as 24 times q1 plus r1, and aj can be represented as 24 times q2 plus r2. Any number can be represented. This is basic division algorithm. Any number can be represented in terms of like dividing by any numbers. Let's say 24. We are dividing here by 24, right? So we can divide. This is a1, this is a2, and this is a sum. This is a sum. This we want to be divisible by 24. These two part, sum is divisible by 24, obviously, because both are multiple of 24. So these two are divisible already. We have to take care of r1 plus r2. And r1, r2 are remainders. If you think about it, the r1, r2 are remainders. So r1 and r2 both obviously are less than equal to 23. Because if you divide by 24, how you cannot get a remainder more than 24, or even equal to, or you can get a remainder 0. So if you think about this, we need r1 plus r2 should be divisible by 24. So the whole sum is divisible by 24. Right. So r1 plus r2 can be, both can be 23 at max. So that can be 46. So we only have, actually, we only have two possible sums of r1 plus r2. r1 plus r2 can be equal to 0, or r1 plus r2 can be equal to 24. These are the only two possible sums that we have, because it cannot reach to 48. In these both two cases, we can get the pair to be divisible by 24, right? So we need to now look at, so this, if you think about it, this, what is this condition? The second condition is just that if this number has a remainder 1, then this number has a remainder 23. So it's just the opposite remainder. Opposite remainder meaning the number minus the remainder of the other number. That we need to find. So let's say we are at the index I. So we need to find number of numbers who gives remainder this. We need to find all the j's before this current I, which give a remainder this. So we can store all the remainders of each of the number behind in a map. Simply we can do that, and we can go through. We can ask the map we need this current pair. We need this. How many people are there with this remainder? This remainder. We need this remainder, right? And in this case, this is the other case. R1 plus R2 equal to 0. So The only thing is their both should be equal to 0. Otherwise, how it's possible? So in this case also you can actually cover this if you take a modulo 24 here outside this also. Then you can cover this case inside this case only. So 24 minus vi modulo 24, let's say is 0. We need the other number to be 0. So this part becomes 0. 24 modulo 24 also gives 0. Right. So this can actually cover all the cases. We'll go through the solution now. So the solution is simply what I told here. We'll go through each number and we'll go through the what we require as the other numbers remainder. We require 24 minus the current numbers modulo by 24, and we have to take modulo by 24. Let's say this IT modulo 24 becomes 0. 24 minus 0 will give us 24. So 24 is not really possible to remainder, so we'll just take the remainder by 24 here. And then we'll store the remainder of this current number in the map, so the numbers in front can use it. That's a great. Thank you for saying. So this is our question. We are given power array where each element represents the damage of a skull, and we have to cast the maximum possible damage. If we use some particular damage, we cannot use damage -1, damage -2, and damage +1 possible. So we have to tell how much maximum damage we can cast. Let's say in this first example, they tell 1, 1, 3, 4. In this you can use, if we use 1, we cannot use 3 then because it's +2 of the first two. So we cannot use that. Right. So in this, the maximum possible answer is 6 by taking 1. And this one also we can use because you can use all the power of 5 whatever you've taken. And then they've used 4 because it's +3, not +1. So the +1 or +2. If it's +1 or +2, you cannot use. The maximum possible answer is 6 here. In this case, the maximum possible answer is by using 166. So if you think about it, if we randomly go about it, we cannot actually, we'll have to go backward in the array, forward in the array. If we start from power I, let's say we use a power of I, then we have to mark somewhere that we cannot use power of I -2 and power of I -1, which is somewhat tricky if you can't try to do it like this only. So it's actually better to sort the array initially. We can sort this array and we can handle we can handle it like in a DP question, right? So of what's considered, we have this. Uh, Firstly, we'll sort the array because you can use any power that you have to introduce. That you can use any power if you want. And this is like a take not take DP. We can formulate this question as a take not take DP. Let's say we have some values A1, A2, A3, A4, and these are sorted. We can just sort this array. And whichever we are going to formulate a DP solution here. How can you think of a DP solution? Let's say we are going to use a particular value A1. This is the smallest value in the array, sorted value. If we use A1, all the numbers which are A1 +1 or A1 +2 cannot be used. So all the values behind that will not consider because it's the first value. It's the first value in the sorted array. So let's say A2 and A3, this is +1 and this is +2. We can consider how many times A1 comes. A1 times its count A1 plus what is the answer of this part. Right. If you think about this, you can independently solve this problem from here to here. A2, A3 and A4. You can independently solve this problem from A4 and ahead. So we can say DP of A4 in this case. Right. Let's think of this. This is the DP of initial value. This is DP of 4 again. So this is DP of 1. In this case, in this particular case, when this value is A1 +1 and this value is A1 +2. So what I am saying is, if we consider all the numbers in increasing order, you can formulate this kind of DP in which you skip all the values which are A1, AI +1 and AI +2. So let's say we are standing at index I. we can do two things. Either we can take it or not take it. If we take the value, we can do how many times this AI comes, count of AI into AI plus will come to this part. And if we do not take this value, then we can go ahead and just do this thing dp5 this one. Right. So let's say number comes four times. Uh, let's say the number four comes three times. Let's say this. So we'll use how many times if we are using this power. If we are using four, we'll use how many times the four counts. We'll use all of it. Right. If you count it normally, then it can give you tail. We can use a map for this. So we can say count of AI, how many times AI comes, plus let's say this value is 5, 5, 6, 7, 8. If we are using 4, we cannot use 5 and we cannot use 6 because it's nums of I plus 1 and this is nums of I plus 2. Right, so we cannot use this value. So let's say the next index from which we can actually use the values is next. So we can formulate it as TP of next. So this is a take not take TP simply, in which if I take a value, then I'll take all the occurrences of that value, how many times it's coming, plus I'll go ahead from there to the place where we can again solve this problem recursively, like in a DP fashion. That this is a individual problem. It does not depend on this initial part. This problem from here, let's say 10, whatever, then 11, 32, because this I have sorted it already. So whatever the values are there, if you've sorted it, then you only have to take care of the condition from one side. If you use the power of I, you cannot use power of I plus 1 and power of I plus 2. You do not have to consider power of I minus 1 and I minus 2 because you will never come to an index which you cannot use. If I'm at the first index, I can use it obviously. If I have to use the value power of I plus 1, I'll go through the case of dp of I plus 1, right? That we are not going to use this particular value, but in the TP of I plus 1, then you can use nums of I plus 1. So it's basically that key. If you use a particular value, skip all the values which are greater than it, which you cannot take after that. So you cannot take 5 and 6. So skip those values and whatever you land, wherever you land is the next index. From there, you can recursively solve this problem again in a DP fashion. You can say this index as next. So when we can say count of AI into AI plus DP of next. And when we not take, we can do DP of I plus 1. So you can take max of these two. That should be the solution for the question. Why we are sorting again, I'm trying to simplify it, that if we do not sort, how can we like nums of I minus 1 and nums of I minus 2, you'll have to take care also because they can be anywhere. But if you sort, you only have to uh, think of the forward conditions because we'll only come to an index if we can use it. If I cannot use 5, if I've used 4 and I cannot use 5, I'm skipping 4. I'm going directly to, I'm skipping 5. I'm going directly to 7. The value which I can use. I'm going directly to DP of next. So, so this is how we have to do this question. This is a simple DP solution. Okay. So the solution is here. I actually firstly did a lot of this in recursive manner. If you do it in recursive manner, it's giving a TLE, I don't know why, but it does. I change it to calculational to work fine. So, firstly, let's understand by, the recursive method because that's a bit easier. Uh, for each DP of I represent how much you can take from I to the last index. What is the maximum possible answer? So if I is at the end, we can just return 0. If it's already calculated, we can return that. Now I need to go to the position of power of I plus 2 just greater than that because we need to go to the next position. This is the next index. So how many times this number is coming? Times power of 5. Plus you can go to the next position, right? Which I was telling you. From here after the point you should go to uh, where you can DPF next. Or we can use DPF I plus 1. DPF I plus 1 or we have to take the max of both of these, right? So this is the same thing in tabulation, and this works, but the recursive flow does not work. It gives TR here on one, but right. So first we will sort the input, then we will count frequency of each value, then we will make a DP array. DP of n is equals to 0. You have to set this because the last value, the answer is 0 at the last. Next from n to n, how much you can make maximum value, that is 0. So we'll start from this dp of I equal to n minus 1. From I minus 1 equals to 0, we can start from the end because we are filling in the tabulation. We are filling the bottom of. So we'll it's the same code that was written in the recursive manner. We've just copy pasted it here. So we have to return dp of 0 for how much maximum levels you can do from 0 to n minus 1. Frequency of I into power of I plus dp of next and all max other values equal to 5 plus 1. We have to take maximum loss what of this. Thank you. So this is the last question of the weekly contest. So we're given an array ARR and we peak they have defined peak is as being simply like the value which is greater than both its neighbor AI. If it's greater than AI of AI minus 1, AI plus 1 both, then it's a peak. So initially we're given an array. Then we are given queries of two types. First query, we have to determine the number of peaks in the subarray Li to Ri. And we in the second query, we have to determine the number of we don't have to determine anything, we just have to change the value and update the value of the index they have given to the value of L. Right. So the first and last element cannot be peak. That is obvious. That a single element can never be a peak. We have given that already. They've stated that. And now, if you think about this is a hard problem, but it is quite simple. Like it's a direct application of segment tree. If you want to do it by that way, there are multiple methods. I've actually not done segment tree. I'll come to my solution in a minute, but the segment tree solution is quite easy, so we'll go through that firstly. So initially we're given an array A1, A2, A3 to AN. We're given this. And in the second type of query, we'll change some values. We'll change this to let's say some AK or some any value, not even in this array, just some value K you can say change it to. Right. So you don't have to confuse it with any value of the array. So they'll change it to any value and then they'll give some range, any range L2R. This range they can give, some bigger range they can give. They can give the whole array range and they want the number of peaks in this part L2R. Right. So we can maintain simply a segment tree which will maintain all the particular peaks. So we can maintain a segment tree and let's say we have to query from L to R. Right. And if we have to query from L to R in the segment tree, then rather than querying from L to R, because let's say the index AL is a peak in the original array. And will it be a peak in the subarray from L to R? No, because it's the last value. It can never be the peak. So if we are given uh, the values L to R, we should actually query the segment tree from L plus 1 to R minus 1 because last values can never be a peak. If we should return the number of peaks in this range rather than L to R exactly because the last values cannot be a peak in the subarray, but they can be peak in the original array. So basically, we can maintain a segment tree, and when we are filling the values at the end position, like if S is equals to E, the building thing, what is the building criteria of the segment tree when we are building it? If S is equals to E, then we should check if this value is a peak. So we can check is a peak or not, is peak. If it's a peak, then we can return 1 from this position. How can we check if it's a peak? AI greater than AI minus 1. A basic knowledge in segment tree is required in this. If you don't know how to make segment trees, then you obviously cannot do this question. But you can do this question in some other way, which I'm going to do now. So this is basic segment tree solution, which I'm not going to show because I've not implemented this, but this is also quite easy to implement. I'm going to show what I have done in this, which is I've used an ordered set. Okay. So basically, initially we're given the array, right? 8, 1, 8, 2, 8, 3, up to n. Now I'll go through the array initially and I'll maintain an ordered set in which I'll keep the peak indices, all the indices which are peaks, right? So we can put all the indices which are peaks in the ordered set. Why we're using ordered set? Why not simply set? I'll tell that in a minute because you cannot actually find how many elements are there, like greater than n or less than n in the range. So let's see. This is the whole array. We have maintained an order set. Initially, I've kept all the peak indices in that. Now, if a query is of type 1, then simply we need to find the number of peaks in range L to R, right? So what we can do, we can find the number of uh, indices which are inside the ordered set in the range L to R in ordered set. In the ordered set, we can find all that. We can use order by key. We'll come to the implementation in a minute. We can find all the number of peak indices in L plus 1 to R minus 1. Actually, it's the same thing here. The last indices can never be the peaks. It is given in the question itself. So we need to find number of people in the ordered set L plus 1 to R minus 1 because I'm keeping all the peak indices in the ordered set. This is the first thing. Now we have to actually, the main point is how to handle the type 2 query in the ordered set. Type 2 query is he will change the value at a particular place, right? So if let's say we are changing at the index I, we are changing the value at index I to val. We are making it val. Look at the index I minus 1 and the index I plus 1. If you think about this, if we change the value at index I, it can change the index. It can either, maybe this was peak earlier, it will change from peak. Maybe this was peak earlier, it will change from peak. It might not be peak earlier, now it might become peak. So it can only change the peak condition at 3 different indices, I minus 1, I and I plus 1. Right? If we are updating an index I, if we are updating index I, and it can change the peak condition at index I minus 1, I and I plus 1. Right, so it will only affect these 3 values if you think about this. So if these values are already in ordered set, I'm going to remove them initially. I'll go through all type 2 queries and I'll go to the array and I'll remove the value I minus 1, I plus 1 and I from the ordered set initially. Then I'm going to assign this value val because they have given it to update. We'll update this value to val. Now I'm going to check the condition for peak for the index I minus 1, I plus 1 and I. So you can check the condition again, and if it's again a peak, you can put again in the ordered set if it comes out to be peak again. So basically what I'm doing for the second type of query, if they are saying to update index I, index are given I, then if I minus 1 exists in the ordered set or I plus 1 exists in the ordered set or I exists in the ordered set, remove all of them and say that you cannot be peak right now. We'll check it again if you're peak or not. We'll remove I minus 1 and I plus 1 if they are already peaks. Then after assigning this value whatever we are given, we are said that we should assign this value as well. We'll assign it well, and then we'll check the condition for I plus one, I minus one, and I again. Are they peaks? If they're peaks, again I'll put in the ordered set. So we have maintained the type 2 query also. So how can we do this in the code? Simply we can go through here. So I made a ordered set. We have to use the ordered set. We cannot just use a set because we need to use the order by key function. If you do not use order by key, right? So we cannot actually use a normal set because we need order by key. So I've just used a normal snippet for the orders. Like order set, you have to know this already. You can check it out from GFC or anywhere. So I made a order set, and I'm going through. Initially, I'm keeping all the peak indices inside there. Now I'll go through the queries. If the query is of type 1, and if there are only two values, let's say L R is equal to L plus 1, then there are only two values and none of them can be peak because both values are at the end. So if like the L and R are like at a only difference 1, so there are at most only two values, then obviously the answer is 0. Then we're continuing. Otherwise, I'm doing I think I've messed this up. Okay, this is it. So we are going to the index R minus. So order by key function gives the value which are strictly lesser than the value we are giving. So if I'm giving input as RA, right? So it will give all the values which are strictly lesser than that, right? Alright. And same here in the IT plus one. If I give IT plus this L, IT of one is L. So we are giving L plus one. So it will also remove if there is L. We will not consider the end values, right? So we will only consider from L plus one to R minus one. If I do IT of L plus 1 here, then it will consider L as out of the bound. It will not be considered in the answer. So this is just basic L plus 1 to R minus 1 query in ordered set. For the second part, I'm first assigning the value, whatever we are given in the question. Like in the query, whatever we are given, I'm assigning the value. Then if ordered set contains the index I minus 1, then I'm erasing it. If it contains the index I, then I'm erasing it. If it contains the index I plus 1, then I'm erasing it. And then I'm checking for all three. Is the condition of peak hitting here? Is it becoming a peak now? If it's becoming a peak, I'm again inserting inside the order set. And at the end, I'm just returning the answer. So yeah, that's it. You can just run it once and see if it works. Yes, it works. So you can do a segmented solution also, which you can go through the solutions in the leak code here. That is also fine. This is also fine to do anyway. Thank you for this.